Hi guys, today I'm going to be talking about airflows on different objects. I'm going to be talking about 3 objects in this video. The first object I'm going to talk about is a circular cylinder, similar to this candle I have here. The next object I'm going to talk about is a square cylinder, kind of like this contact lens box I have here. Alright, so the final object is going to be an airfoil, which I don't have, so I drew a picture of what one looks like. So just try to imagine what this would look like in a 3D kind of way. Don't mind those. So for the cylinder, what we did was we marked a single point on the cylinder, and we said that was going to be where we're going to measure the pressure at. And so as we pushed air down on top of it, we rotated the cylinder slowly, and we saw that as the cylinder rotates, the pressure decreases right here, and then as it goes all the way back around, it goes back to the same value as that when it first started. So for this one, like I said, we were doing the square one. So again, we pushed air down on top of it, and because it's not symmetrical, we had to measure the pressure at a bunch of different points. So as we were twisting it, or changing the angle of it, we saw that the pressure changed on those points. But the really important thing that we saw was that when it's at 0 degrees, the drag coefficient is less than when it's at 45 degrees, which means that it's easier for air to flow when it's tilted like this at an angle versus when it's straight up like this. And for the airfoil, like we discussed, I don't have that, but I can tell you that when we did the test on it, we saw that as we twisted the airfoil like this, we saw at some certain angle, which we found to be about 24, 26 degrees, the airfoil loses a massive amount of lift, which means the air that's pushing up on it, we saw that it loses all of that at about 24, 26 degrees. But then as we twisted it back, it regained it at like 11 degrees. So in our data, we found that we had a coefficient of drag of about 1.1, and we had a Reynolds number of about 50,000. So that means our point would have fallen right over here on the chart, which is exactly where it needs to be. So like I told you guys earlier, it's easier for the air to flow when it's at 45 degrees than 0 degrees. And to back that up, we have the data from the lab. We found that the drag force on 0 degrees is 0.93, and its coefficient of drag is 5.877. And then for 45 degrees, we have 0.77 newtons as the drag force, and a coefficient of drag of 4.866. And like I explained before, that makes sense because of the angle, and it's easier for the air to flow over it. And here, it's just pushing straight down on the flat surface. And when we were comparing the two, the cylinder and the square, we saw that the coefficient of drag on this was much less, and so was the drag force. Thank you guys so much for watching. But before you go, I have a brain teaser for some of the more experienced people here. In a 50-mile-per-hour wind, what is the total drag force on a 30-foot vertical flagpole of 4 inches diameter? And then I want you to tell me how that Reynolds number compares to the one from our lab.